So I want to sort of go into the meat of non-interactive zero-knowledge proofs from Bilinear Maps. This is a winter school, so I don't actually assume people to know pairings already. I think a lot of you do know pairings already. If you know pairings already, I apologize in advance. You could have slept for half an hour more in the morning and you would not be losing anything. But do forgive me, I wanted to be accessible to everybody, even those who have not seen pairings before. And I want to kind of get our hands dirty as well, because this is a winter school, so there will be exercises along the way, so please do find pen and paper. And we'll take a couple of breaks along the way for some small exercises. Okay, so I want to start with bilinear maps, what these kind of things are. So I'll be working in this talk with a setup that describes a prime P, three cyclic groups of prime order P, G1, G2, and GT. We usually call G1 and G2 the source groups or the base groups, and then GT for the target group. And mathematicians often write a G1 and G2 additively, but I'll use multiplicative notation, which is more common in cryptography. I'll assume G and H are generators of the two source groups. And then the special thing we have in the setup is this map, E, that takes two source group elements and produces a target group element. Okay? And the bilinear map applied to the generators G and H is non-degenerate, okay? And since the target group has prime order P, that means that the pairing of G and H is actually a generator for the target group. And then it has this bilinear property that if you take G to the A and H to the B and pair them together, you actually get the generator of the target group raised to A times B. Okay, so what can we do in this group here? So first of all, I'll assume that there's a canonical unique representation of all the group elements. So if you want to compare two group elements to see whether they're the same, you just compare the bit strings and check whether the bit strings are the same. So that's an easy operation to do. And then I'll assume that we can decide very efficiently membership of the group. So you get some bit string, does it represent an element in the group? Easy to decide. I'll assume that it's easy to compute the group operation. So if you have two group elements, you want to multiply them together, that's an efficient operation you can do. And then I'll also assume that it's efficient to evaluate this bilinear map, so you can compute the pairing quite easily. And I'll refer to these as the generic group operations. Okay, so usually these groups are subgroups of elliptic curves or finite field or an extension of a finite field. A target group is typically a multiplicative subgroup of some large field. But it doesn't really matter too much the mathematics, and I'll not go into the mathematics of pairings. I do want to distinguish between three types of pairings, though. Classification due to Galbraith, Patterson, and Smart. So they distinguish between a symmetric setting, where the two source groups are the same, an asymmetric setting, where they're not the same, but there's an isomorphism between, so of course all the groups have prime order P, so they're all isomorphic to each other. But in one of the directions, from G2 to G1, it's actually efficiently computable. Okay, and then there's another asymmetric setting where there's no efficiently computable isomorphism in either direction. And it's this latter setting, the type 3 setting, that we'll be using in this talk here. And I think in general is the one that people should be using because those are the most efficient groups with the smallest elements and the most efficient computation. Okay, so and in this setting here. So typically what we have then is, if we think of field elements modulo p, then they're typically smaller than any of the group elements. And then usually you consider G1 to be the smallest of the groups. So there you have more compact group element representation than in G2, and the worst one is GT. And if you look at the cost of computation in these groups, it's sort of the same pattern that comes into play. So if you want to do field operations, that's not so expensive. Multiplication of group elements in G1, bit more expensive. Even more expensive multiplications in group 2. And the most expensive group operations are in the target group. And if you look at all the possible operations you can do, the most expensive one is a pairing of 2 group elements. Okay, so for those of you that have not done anything with pairings before, came up with some exercises to familiarize yourself with the operations and get used to the notation. So I'll set aside 15 minutes for this exercise. If you already worked a lot with pairings, maybe this is a pretty straightforward exercise, but then find some good research questions or find some tough questions to ask me in this talk. Okay, so let me present my own solutions to these, aside from a typo that some of you were so kind to point out to me. So for the first question, which groups these belong to, so the implicit assumption is that the left side of the pairing is elements in source group 1, so U would be in source group 1. And then on the right side, we have the source group 2 elements, so that would be V and W. And then Y and Z would belong to the target group because that's where the pairing maps to. And A is a field element, so an element which is an integer, but then unique up to isomer, up to modulo P. For the second question, if you see this pairing of U with U, then that would indicate that U is both an element in source group 1 and in source group 2, so that's probably the setting where the 2 source groups are identical to each other, so that's the type 1 setting. And for all these reductions, so we had first the pairing of G to the A with H, and then G to the B with H. And using the bilinear property of this map, that's the same as the pairing of GH to the A and the pairing of GH to the B. And then that gives us the pairing of GH to the A plus B. If we look at the second one, it actually turns out to be the same because of the bilinear property. So in both cases, we could pop A out to the target group exponent and B out as an exponent in the target group, and then we get the pairing of GH to the A plus B. Okay, for the third equation here, I somehow accidentally replaced the G with an F. So, but for this particular equation in the solutions, we get the pairing G to the A and H to the minus B. There you can pop out the exponents and get the pairing of GH to the minus AB. Of course, this is a cyclic group, so the elements commute. It's abelian. So you can swap around the pairing of UV and GH to the C. And then as a result of that, you get the pairing of GH to the C minus AB and the pairing of UV. And for products of pairings, again, we can pop things out in the exponent because of the bilinear property of the map. And we get the pairing of GH to the sum of the AIs and BIs. Now, once you've done all these reductions, they look nice mathematically, but you could ask from a computational point of view, which one is the more reduced version of these, right? Because if you have the pairing of GH to the AB, that's the same as the pairing of G to the A plus B. with the h, or the pairing of g with h to the a plus b. And you can ask which one of these is the more reduced one. They sort of like mathematically are the same and look equally simple, but perhaps one of them is more easy to compute. And I guess in general, the first one would be the easier to compute because the source group 1, we imagine, is the smallest of the groups the groups where the elements have the smallest representation as bit strings and the most efficient computations. So it would be the easiest to compute g to the a plus b in this group. In practice, I guess, on the other hand, often g and h will be fixed and used many times, so you can actually pre-compute the pairing of g and h. And then you just need to do an exponentiation in the second group to compute the pairing of gh to the a plus b. Okay, and if we have group elements, of course we can write out these group elements as some g to the x for some x, v and w as h to the y and h to the z. Now we know these exist, but they may not be efficiently computable. In general, we'll assume that it's hard to compute these discrete logarithms. But of course, we can operate them mathematically. So if we plug those into the expressions, we can see that we can simplify the notation quite a lot. So the bilinear properties will give us that the pairing of u with v and multiplied with the pairing of u with w is the same as the pairing of u with v times w, right? So that's linear property in the second coordinate, and you get the corresponding linear property in the first coordinate, of course. For the last of the reductions, we have pairings of u to the a and vi to the b to this c divided by ab. Of course, I'm assuming here that ab is non-zero. So by the bilinear property, AB would pop out of the pairing. They would cancel out with the division of AB, so you just have the pairings of U and VI to the CI. And that one you could, again, do some arithmetic on, and you could pop it inside with the linear property. So you would get the pairing of U with the VIs raised to the CIs. And for the final question, if we have the pairing of U and V is the same as 1, well, if we rewrite the pairing of U and V, that's the same as the pairing G and H to these secret discrete logarithms X and Y. Okay, and 1 is, of course, since the pairing of GH is a generator for the target group, that's the same as that generator raised to 0. So if the pairing of UV is the same as 1, then that means that XY is 0. And that, of course, implies that either X is 0 or Y is 0, and therefore either U is 1 or V is 1. Okay, so I think and hope at this stage that you are familiar with the operations on the pairings. And let me then state the assumption that I'll be working on. So as I said, we are assuming that we're in a type 3 setting, so there's no efficiently computable isomorphisms between the two source groups. And in that setting, it's reasonable to assume that the decision Diffie-Hellman assumption holds in both of the source groups. So in other words, I'm assuming that if we have an attacker that has full knowledge of this setup, so throughout I'll assume all algorithms know these primes and the groups and the generators G and H. Okay, and if we assume this attacker here then gets 3 group elements, U, V, and W, where U is some random G to the X, V is some random G to the Y, and then this attacker is unable, it's infeasible to figure out whether it gets W, which is either x time, g to the x times y, or g to some completely random element. So it cannot distinguish between getting g to the xy or getting a random group element. And I'll assume this holds in both the source group 1 and in source group 2. And why will I assume that? Well, of course, one of the things we want to do is Elgamal encryption, right? So, so the setting here is that we generate a public key, y, which is g raised to some secret exponent x, and x is then the secret key. And to encrypt a group element in the source group, we then pick a random r and encrypt the message m as g to the r and y to the r times m. And of course, you can decrypt that by computing on a ciphertext u and v, v to the u to the minus x. And if you plug that in, in the encryption above, you see that you get exactly m back. And we know that this is indistinguishable under chosen plaintext attack if the decision Diffie-Hellman assumption holds in source group 1. And of course, you can then do Elgamal encryption in source group 2 in a similar way. So that's sort of the tool I'm going to be using a lot in this talk, and nothing else really. Okay, so now let's get to the fun part and talk about pairing-based proofs. Okay, so I'm going to talk about Growth-Sahai proofs. If you're in doubt, I just mispronounced my own name here. It's really Growth-Sahai proofs, but nobody can pronounce that, so I've given up and I call them Groth-Sahai proofs as well. So the setting in Groth-Sahai proofs is quite simple. Consists of 8 group elements, 4 from source group 1, 4 from source group 2. And they can be set up in 2 different ways, okay? So this is really what we call a common reference string, something that sort of bootstraps and enables us to do non-interactive zero-knowledge proofs. And either it can be set up such as a binding common reference string. And when it's a binding common reference string, you get proofs that have perfect completeness and perfect soundness. You can also set them up to be a hiding common reference string. In that case, you get proofs that have perfect completeness and perfect zero knowledge. And the cool thing, and this is where we leverage the decision Diffie-Hellman assumption, is that you cannot, as an attacker, distinguish between these 2 setups. So you don't know whether you're looking at a binding common reference string or a hiding common reference string, right? So now you sort of get the best of both worlds, because if you're in this setup, you know that it's a trusted setup, that it's been put up in a nice way. You would sort of trust the soundness from that, right? And nobody would be the wiser. But in some sense, it's not revealing anything about the witnesses, because it could have been a hiding common reference string. Nobody can tell the difference. But if it was a hiding common reference string, it could not reveal anything about the witnesses that you use. So it's actually a very kind of clean framework you get. I have sometimes referred this to as a sort of a stricter form of zero knowledge called composable zero knowledge, which says that so traditional definition of non-interactive zero knowledge talks about that you can simulate the common reference string and the proofs together. But in some sense here, you can sort of split it up in saying, one thing is we can simulate the common reference strings, right? It can be either binding or hiding. And then once you have a hiding common reference string, you actually have perfect zero knowledge. So even if you know the trapdoors and things like that, you would not be able to distinguish between real proofs and simulated proofs. So it gives you a slightly stronger flavor of zero knowledge. Yeah, so I call it composable zero knowledge. And the origin for that name is because when you have this sort of strong zero-knowledge property, there's some way situations where it becomes more easy to compose zero-knowledge proofs in security proofs, because you have this property that once you have a hiding comma reference string, it's perfect zero-knowledge, so you can even reveal the simulation trapdoor and it's still zero-knowledge. So it makes life easier in some security proofs. Okay, so then which kind of statements can we prove, right? So now it gets a little complicated. So we're going to look at instances that have a lot of equations, okay? So let's say we have Q equations, okay? And all of these equations will be over some variables. And think of this essentially as trying to say, formulate any kind of statement you could be interested in when you're working with a bilinear map, right? So when you're working with a bilinear map, you have all these generic group operations, right? So you can multiply group elements together. You can pair group elements. You can work over the field, right, and add and multiply field elements, okay? And then what are the kind of equations that we could build using those operations, right? So one class of operations we could build with that would be pairing product equations. So essentially you take group elements, you pair them together, you multiply them together, and in the end you kind of compare some of these target group elements and see, did you get the same thing, right? So that's the first class of equations, the pairing product equations. It says we can pair group elements, okay? And it could be known group elements, so A, B, think of these as known public group elements. And you compare them with secret group elements. So think of X and Y as the secret variables that these equations are over. Okay, so you can pair known elements with the secret Ys. You can pair the secret X's with known public elements, or you can pair secret elements with one another and also raise them to some known power, gamma. Okay, so you can do that with a bunch of elements. You can multiply them all together once you mapped it to the target group. That's also generic group operations. And the question then is, do you get 1 in the end? Okay, so you can imagine having several of these pairing product equations. You could also imagine creating equations resulting from exponentiations, right? So you could take known group elements and raise them to secret powers, the yj's, and secret group elements, the xi's, and raise them to known powers, bi. Or you could take secret group elements, the xi's, and raise them to secret powers, the yj's, and again modify that with some known exponents, the gamma ij's. Okay? And you do a lot of these exponentiations of known with unknown, or unknown with known, or unknown with unknown. And at the end, the question is, do you get this result, this t here, which is a known element? Okay? If you have exponentiations with knowns, that you can fold into the t. And if we're looking at the field operations, right, you could imagine taking knowns, multiply them with unknowns, and you can do that both on the left side or the right side. Or you can multiply unknowns with unknowns, right? And again, the question is, when you then add up these products, do you get this target T? Okay, so you have these 3 types of equations that express all sorts of operations you can do with the generic group operations. Okay, so really the set of quadratic equations in some sense, right? Over the binary group. And the question now is there some witness? Okay, so you see this instance, all these equations over these variables. Okay, and the question is there some witness, some assignment to these secret group elements in source group 1, secret group elements in source group 2, and secret field elements, such that this assignment would satisfy all of the equations simultaneously. Okay, and this is what we want to give non-interactive zero-knowledge proofs for. Okay, so let's dig a little into these statements and see what we can say about them. And the first thing I want to think about is, of course, whether they are NP-complete. Right? So can you express any statement in NP using these equations? And the answer to that is yes. Okay, so let's take our favorite NP-complete problem, satisfiability. Okay, so we have a bunch of clauses. We want to show that they can all be satisfied with some variables, x1, x2, and so forth, which can be either true or false. Okay, so let's try to reduce this set formula to something which involves these equations. And particularly, I'll just reduce this to quadratic equations. So the idea is that you will encode true as 1 and false as 0. Okay, and essentially you want to then convert this set formula into an instance that says all of these variables are either 0, 1, so they represent proper truth values, right? Either correspond to true or false, but we don't have a variable which has assignment 3 because we don't know whether 3 would correspond to true or false. Okay, and second, we would want to encode that all of these clauses should be satisfied. Okay, so for each variable, we can set up an equation, x1 times 1. So this is an unknown with a known, right? Plus 1 times y, so that's a known with an unknown, should be equal to the target 0. Okay, so that's on the form of quadratic equations. And the second equation we can set up is that xi times 1 plus xi times yi should be equal to 1. And that's also on this form of a quadratic equation. Okay, so if we do that for each variable, then the first equation, right, that will give us that yi is equal to minus xi, assuming that these two equations hold. And if you then take that and you plug that into the second equation, you get that xi times 1 minus xi is equal to 0. Okay, and if you have xi times 1 minus xi is equal to 0, then there are only two solutions to this quadratic equation in modulo p, right? Either xi is 0, which would correspond to in our interpretation that it would be false, or it's 1, which in our interpretation would correspond to this being true, right? But all the other options are ruled out. It's not going to be 2, 3, or 4, or anything else. Okay, so those equations guarantee that all variables now encode proper truth values. Okay, and the second question now is, are all the clauses satisfied? And for each clause, we will then simply introduce a quadratic equation that involves an extra variable. So let's call that y prime. Okay, so for instance, if we look at the first set formula, we have x1 or not x2 or x3. Okay, so we'll encode that with a quadratic equation as x1 plus 1 minus x2 plus x3, and then multiply that with y1 prime and demand that this should be equal to 1. Okay? So why do we demand that this is equal to 1? Well, because if the set formula is satisfied, right, then at least one of the literals will have to be 1. In that case, we get a sum which will be non-zero. Okay? It could be 1, it could be 2, it could be 3. And in that case, it actually has an inverse that's going to be the y1 prime that testifies to the fact that this is non-zero, and that will give us 1. If, on the other hand, for one of the clauses you have that it's actually not satisfiable, right? That means that you would actually have something that adds up to 0. Okay? In that case, no inverse will exist. So if you can satisfy all these equations simultaneously for all the clauses, that means that all of the clauses will have at least one non-zero truth value, and in other words, the OR of them will be true. So what that shows is that the statements, we can formulate this system of equations over the bilinear map is actually NP-complete. Okay. Now, we can also do things that are sort of a little closer to cryptographic operations. So cryptographers like to work over finite fields. So what if we take an arithmetic circuit over ZP? Okay, so an arithmetic circuit over ZP looks something like this. It has some addition gates modulo P, some multiplication gates modulo P. And you could imagine the instance describing how this circuit is wired, what the gates are. It might describe some of the inputs and the outputs. And then the claim is that there's a witness corresponding to the rest of the wire values such that everything is satisfied and all the gates are respected. And again, it turns out that you can reduce an arithmetic circuit to a set of quadratic equations. Right? So in this particular case here, if you look at the addition gate, so x1 plus y1 should be equal to x2, right? That's something you can encode with the first equation here. And if you look at the multiplication gate, x2 times y1 should be equal to 0. That's what is encoded in the second equation. And in general, when you have more larger and more complex arithmetic circuits, again, you can easily encode them with quadratic equations. So that shows that the quadratic equations also allows us to describe in a more direct way satisfiability of an arithmetic circuit. Okay, so that shows that these Growth-Sahai proofs are NP-complete and capture general computation. But the real reason that they're interesting, I think, is for practical purposes, right? So when you're constructing a practical cryptographic protocol, you're perhaps not so much thinking about, I want to prove some general NP-complete statement. You have something much more concrete at hand, right? You're sitting, you're designing group signature scheme or something like that, right? And you want, have various cryptographic tools, and you want to prove something about these objects that you are constructing. So such a statement might, for instance, be something along the lines of, here's a ciphertext, and I claim inside this ciphertext is a plaintext, which is really a signature on this message here. Right? And that's the kind of thing you want to prove when you're constructing cryptographic protocols. Okay, so let's take a statement like this. So suppose we have an LGML ciphertext, U and V in source group 1 under some public key Y in source group 1. And suppose the claim is that it encrypts Bonnet-Boyan signature on a message M in ZP. Okay, and a Bonnet-Boyan signature is on the form, the signature sigma is G to the 1 over X plus M for some secret signing key X. Okay, and you can verify it with this verification equation. If you pair the signature with W times H to the M, then that should give the pairing of G to the H. Okay, and the public signing key is then W, which is H to the X. Okay, so if you have the claim over these that this El Gamal ciphertext encrypts a Bayesian signature on this message M, right? That you have an instance that can be described with all these group elements: UV, the El Gamal ciphertext, and the El Gamal public key, and the signing public key, and the message M. Okay, and the witness then is this randomness used in the El Gamal encryption. That is not something that's known to the verifier. And the verifier also doesn't know this secret signature because, well, it's encrypted, right? Okay, and it turns out that this is the kind of thing you can also encode with these 3 types of equations: pairing product equations, multi-exponentiation equations, and quadratic equations. And I've made that an exercise. So let's take 10 minutes.